Hello friends, welcome to Learner's Planet. I welcome you to this very first theory session for D and F block elements. So what are D and F block elements basically? We have discussed about them in our topic for periodic classification and in the periodic table. What are these elements? These elements are present between the S and P block elements, and also the differentiating electron enters into the d orbital. There's one more thing about them, that their penultimate d subshell is incomplete, and also in some cases the outermost shell is incomplete. So we'll be discussing about the properties of D and F block elements in this session. See, we are not straight away going to the properties. I'll first tell you about the general properties, like general, first of all, the placements, about the elements, and the general properties we'll be discussing. So let's start our session here. These D block elements are also called as transition elements. These elements, you can say the transition elements, these are the elements which have partially filled d orbitals, either in ground state or in one or more of their ions, right? Their penultimate d subshell is incomplete. Outer shell may or may not be complete. These elements are called transition elements as they are placed between most electropositive S block and electronegative P block elements in long form of periodic table. What are S block elements? That is lithium, sodium, potassium, rubidium, cesium, francium. And the second group, beryllium, magnesium, calcium, strontium, barium and rhodium. So these elements are placed between S block and the P block elements. And also their properties are intermediate between S block and P block elements. These are more electropositive than P block elements, but less electropositive than S block elements. They form ionic compounds in their lower oxidation state and covalent compounds in their higher oxidation states. As the alkali and alkaline earth metals, they form ionic compounds. They've got lower oxidation states. And they form covalent compounds in their higher oxidation states, as the P block elements, which have got the oxidation states of +4. They form the covalent compounds. In all these elements, the differentiating electron occupies n-1 d orbital. But of these students, see zinc, cadmium, mercury, which are present in 2b, which are 2b elements. They are excluded from the definition of transition elements. Let's see why. The definition of transition metal excludes zinc, cadmium and mercury. Why? Because they have got completely filled d orbital. Like say zinc, the atomic number of zinc is 30 and its configuration is 4s2 3d10. Likewise cadmium and mercury, they all have got completely filled d orbital. Their common oxidation state is +2, or they form zinc ++ ions or cadmium ++ ions. Right? That is 2. 2 is its oxidation state. Whereas transition metals, they show variable oxidation states. Like iron, it shows the oxidation states +2 as well as +3. Manganese, it shows oxidation state ranging from say +2 to +7. But zinc, cadmium, mercury, they do not show variable oxidation state. They also do not show characteristics of transition elements like formation of colored compounds. See, cobalt forms colored compounds, chromium forms colored compounds, but zinc, cadmium, mercury, they do not form colored compounds. Even iron, say ferrous sulfate, is called as green vitriol. It forms colored compounds. But the zinc, cadmium and mercury do not form colored compounds. They also do not show magnetic characteristic. They do not show catalytic property. They are not very good catalysts. right? They do not show alloy formation. They do not form alloys also. So these are kept in d block elements because the electron is entering the d orbital. That's it. The rest of, they are not showing rest of the properties of transition elements. Elements of group 3, that is scandium, yttrium, lanthanum and actinium, and group 12, zinc, cadmium, mercury, are called non-typical transition elements. Say scandium also. The atomic number of scandium is 21 and its configuration is 4s2,3d1. It shows only +3 oxidation state. And it is not forming colored compounds also. Right? Now let's have a look on the elements of 3D series and 4D series. See students, these are the elements of 3D series: scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. Their atomic numbers right from 21 till 30. The configurations D1 4s2 till D10 4s2. Now there are two elements which are having anomalous electronic configuration. What is this rule of Bohr principle? What it states that the orbitals of less energy level are filled first, or less energies. The orbitals with less energies are filled first, and then the orbitals with higher energy. In this case, they are not completely filled. See, the configuration is 3d5 4s1. It is not, it should have been 4s2 3d4. 4s2 3d4, but it's not the case because the half filled, say 3d5, the half filled orbital, the half filled and full filled orbital are stable. That is why the configuration or the electron, this enters the d orbital and there is only one electron in the s orbital. Then again is copper. The configuration is 3d10 4s2, 4s1 and not 3d9 4s2. Right? Why this half filled and full filled orbitals are stable? This is because they are symmetrical, and also the lot of exchange energy is released. Because of the exchange energy also, they are stable. See, this is the second transition or 4D series. It is yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver and cadmium. The atomic numbers 39 to 48. The configuration D1 5s2 to D10 5s2. Again, molybdenum is having the anomalous configuration, that is the D5s1. Silver D10s1. Right? This is 5D series, right from lanthanum 57, hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, gold and mercury. The atomic number is 57, and after 57 there are 14 elements which are the F block elements or the lanthanides. That the lanthanides, they are called as what? Inner transition elements, a series within the transition series. And after that is hafnium. The configurations D1 6s2 or D1 s2 to D10 s2. Okay, say after lanthanum there are 14 elements, so that this 4f orbital is filled now, and the electron then enters the 5d orbital. Okay. Next is the fourth transition series, that is the 6D series. It starts with actinium. Remember, actinium and lanthanum, they are not the inner transition elements or F block elements. After actinium, there is 89. After actinium, there are 14 elements. And after that comes this 5F14 6D2 7s2 configuration. So this is actinium and these are other elements. Say after uranium, the elements are scientific or they are synthesized in the laboratories. Okay, so we'll be discussing about these inner transition elements or the F block elements later. Now let's see the properties, the physical properties of these transition elements. We can say the properties in general. That is, we'll discuss about the atomic radii, about their melting and boiling points, about their metallic character, about the ionization energies, and also the variation of these properties along the period and down the group or down in the series. Let's see the general properties of transition metals. First is the atomic radii. The atomic radii and the ionic radii for transition metals are smaller than their corresponding S block elements. Obviously, the radii decreases across the period, right, or from left to right in the period, and greater than their corresponding P block elements. The atomic and the ionic radii for a given transition series show decreasing trend for the first 5 elements and then becomes almost constant for next 5 elements of the series. Let's take up an example here. Say for example, let's take the atomic radii of the elements of 3D series: scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. Their atomic radii are, say, scandium is 144, I'm writing it in picometers. Titanium, it decreases, say it becomes 132. Vanadium is 122. Chromium 117 becomes constant. Magnesium, and this atomic radii is again 117. Iron, it's also 117 picometer. Cobalt 116, it is almost constant. Nickel 115, then again 117 and 125. So what is it saying? That the atomic radii is decreasing and then it is almost the constant. What is the reason behind this? What could be the probable reason? See students, what is happening here? That the electrons are entering the d orbital. So we can say 3d1, this is becoming then 3d2, 3d3, 3d5, 3d5 again, it is 4s1 and it is 4s2. 3d6, 3d7, 3d8, 3d10, 4s1 and again 3d10, 4s2. Now you can see here that the electrons, first of all, they fill the d orbitals and these are unpaired, right? Till say chromium, the atomic radii is reducing. Why? Because of the increase in effective nuclear charge. Got my point? See, as the atomic number is increasing, so the nuclear charge is also increasing. So because of the increase in effective nuclear charge, that is the net force of attraction of nucleus on the outermost electron, it increases from scandium till chromium. It increases thereafter also because the nuclear charge is increasing. But after say chromium, magnesium, what happens? That the electrons have started pairing up. Due to this pairing up of electrons, the screening effect increases. The screening effect means it is the reduction in the force of attraction between the nucleus and the outermost electron. Why? Because of the inter-electronic repulsion. You must have studied about this in your previous class, in the periodic classification of elements. See what is happening? Initially the configuration is coming from D1 to D5 and then again from it is D6 to D10. So what happens initially? The effective nuclear charge increases. That is, a net force of attraction between nucleus and the outermost electron increases till here. There is no screening effect. There is, but it is less. There is screening effect, but it's less. Now, after that, what happens that along the period only in the d orbital, the pairing of electron has started. So what will happen? The inter-electronic repulsion will increase. Right? Due to the increase in electronic or electron-electron repulsion forces. What happens? The screening effect increases. Now both of these are opposite forces. Right? If the screening effect is increasing, the effective nuclear charge will be decreasing. Now students, what will happen? These both, the size of this atom will be the result of the net influence of effective nuclear charge and screening effect both. Right? Now this increased nuclear charge is increasing, right? As the atomic number is increasing. So increased nuclear charge and the increased screening effect, they balance each other. And so what happens? The atomic radii remains constant or almost constant. It increases at zinc. So you can see here, at zinc, the atomic radius has increased. Why so? Because all the electrons are paired in zinc, including the 4s electrons also. So the screening effect is much more than the effective nuclear charge. So the atomic radii increases. Got my point? You can see this graph over here. The atomic radii decreases and it remains almost constant, and then it increases at zinc. Remember, the atomic radii is influenced by two factors. First is the effective nuclear charge and second is the screening effect. Till chromium, see at chromium the configuration is 3d5-4s1. The configuration here is 3d5-4s1 and manganese is 3d5-4s2. Iron becomes 3d6-4s2. So till chromium what happens? This effective nuclear charge increases. And after this, after the pairing of the electron has started, what happens? The screening effect increases. Now the nuclear charge as well as the screening effect are increasing. Right? So both they balance each other, and so the atomic radii remains almost constant, but it increases at zinc because of all the paired electrons. That is, at zinc the configuration is 3d10-4s2. The electronic repulsion forces are high and so the radius increases. Right? Now let's see the ionic radii of these elements. We didn't see what happens down the group. The atomic radii of 4d series are higher than the 3d series. Why? Because the number of shells are increasing. See, the general electronic configuration of 3d series elements is 3d 1 to 10 and 4s 0 to 2. Right? Whereas the general electronic configuration of 4d series will be, it is 4s 1 to 2, sorry. It will be what? 4d 1 to 10 and 5s 1 to 2. So as the number of shells is increasing, so the atomic radii is increasing. But the atomic radii of 4D and 5D series are almost constant. What will be the configuration of elements of 5D series? It will be 5D10, 6s1 to 5D 1 to 10 and 6s 1 to 2. Why it is constant? This can be explained by there is increased number of shells. So if there is increased number of shells, what all orbitals are there? There are intervening f orbitals. Right? There are 4f orbitals also. There is 4f orbital also, or 4f subshell is also there. Right? Now I have told you that the D and F orbital, they have got poor shielding effect. Why? Because these orbitals, they are big in size, the electrons are scattered or sparsely located, and they have minimum repulsion between them, as a result of which the shielding effect is less. When the shielding effect is less, what will happen? The force of attraction between the nucleus and the outermost electron will be more. F orbitals. Right? F orbitals, these are big orbitals. They have poor shielding effect. One reason can be that these are big size orbitals, the electrons are sparsely located, and so there is the less of repulsion between these electrons. That is, the outermost electron, due to these F electron, is facing less repulsion. Right? Due to this poor shielding effect, what happens? This electron is facing less repulsion due to these F electrons, and also the intervening D electrons. Now, what happens that the force of attraction between the nucleus and the outermost electron increases, or you can say the effective nuclear charge increases, as a result of which the size decreases. Right? Now what is happening in case of this 3D and 5D series? They are almost constant. Say zirconium and hafnium, they have almost same size. That is 145 picometer. Their ions also have their ionic radii 80 picometer and 81 picometer respectively. Right? And this phenomenon, say in case of lanthanides, that is say nearly equal radii of second and third transitions elements. It is nearly equal radii of second and third transition series, not the second and the third, that is 4D and 5D, are due to the special effect called as lanthanide contraction. We'll be discussing about this lanthanide contraction in when we'll be discussing about lanthanides and actinides. But the reason is the same. Because of the intervening F orbitals, the shielding effect decreases and the effective nuclear charge increases. Right? The second and the third transition series. So this is how the atomic radii of transition elements varies along the period and along the group. Now let's see the atomic volume and the density, the variation of the atomic volume and density, and also the melting and the boiling points of these elements. See, this is the trend in the ionic radius. For ions having identical charges, that is here it's the ionic radius of M2 plus ion. The ionic radii decreases slowly with the increase in atomic number across a given series of transition elements. So there is a decrease, and again this ionic radii becomes almost constant. You can see this M2 plus ion. Scandium doesn't form Sc2 plus ion, it forms only Sc plus 3 plus ion. From titanium, you can see that there is a decrease in the ionic radii and it becomes constant for a while. Right? It becomes constant. And at zinc, it increases. Here, say nickel, copper, zinc, they do not form M3 plus ions. In case of plus 3 ions, you can see that there is a constant. The ionic radii is almost constant. That is 69, 66, 64 and 63. So do remember one thing, that the atomic radii or ionic radii decreases due to the increase in effective nuclear charge. And in this case, due to the pairing of electrons in the d orbitals, the screening effect is increasing. So the increase in screening effect and increase in nuclear charge, they are balancing each other, and so the radii is almost the constant. Now let's see the variation of their atomic volume and density. See the atomic volume and density. The size of atom decreases along the period, and therefore what will happen? The atomic volume also decreases along the period, and the density will increase along the period. Atomic volumes, they are smaller than group 1 and group 2 elements. Okay, so the size is decreasing, so the volume is also decreasing. If the volume is decreasing, the density is increasing. I'll tell you the densities of the 3D series elements or 3D elements. The elements of 3D series are scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. Now their density, say it varies, like the density of scandium in gram per cubic centimeter is 3.43. Titanium, it's 4.1. Vanadium, 6.07. Chromium, 7.19. Magnesium, it's 7.21. Iron, 7.8. Cobalt, 8.7. Nickel, it's again 8.9. Copper, 8.9, and zinc, it's 7.1. You can see here the density is also still. The density is increasing. But the increase, right, from chromium, magnesium, iron and here, it is not much. The rise is almost constant. It is 7.19, it's 7.21, then again 7.8. The increase in density is not high. Right? Because you can relate this to the size of the atom. The size decreases also, it decreases to some extent and becomes almost constant and then increases at zinc. So the size decreases, therefore the volume decreases, right? If the volume is decreasing, the density is increasing. And do remember, their volumes are smaller than the group 1 and group 2 elements. Now let's check out their melting points and boiling points. All transition elements have higher melting point. Why? Because they are all metals and they've got strong metallic bond between their atoms. So they've got higher melting point as compared to S block elements due to strong metallic bond as well as unpaired d electrons, leading for covalence. See, metallic bonds are also present in S block elements, but in this case there is metallic bond between the atoms and also there are unpaired d electrons, due to which they can share the electrons between them, between the atoms. The sharing of electron can also take place between the atoms. It's not exactly the covalent bond, but sharing can take place. Zinc, cadmium and mercury have relatively low values of melting and boiling points. Why? Due to the completely filled d orbitals, which do not show covalent bonding between their atoms. Say in case of rest of the atoms, like the atoms of iron, the atoms of chromium or the cobalt, right? Here what is happening, or the manganese, they have got unpaired electrons in their d orbitals. So there is metallic bond also, and due to the unpaired d electrons, there is also the possibility of covalency. They are forming covalent bonds among them in their crystal lattice. But in case of zinc, cadmium and mercury, what is the configuration of zinc, cadmium and mercury? It is D10, and S2. So there is, they do not show covalent bonding between their atoms. Melting point of transition metals in a given series increases on moving left to right in a period. It attains a maximum value, and after that the melting point goes on decreasing towards the end of the period. Say till chromium, manganese, they all have the unpaired electrons. They both have, Chromium, the configuration is D5-4s1. Magnesium, it is D5-4s2. They both have unpaired electrons, due to which the covalence between them is more, right? So what happens at the melting point increases, it attains a maximum value and then it decreases. Say in case of chromium, in case of 3D series, chromium has got the maximum value of the melting point. This is due to the fact that strength of interparticle bonds in transition elements is also directly related to the number of half-filled d orbitals. In the beginning, the number of unpaired electrons in d orbitals increases till the middle of the period, that is d1 to d5. After this, the pairing of electrons occurs in d orbitals. An increase in interatomic bonds due to increase in number of unpaired electrons results in higher melting points. See, this is the melting point curve. It is scandium right here. Then is titanium, it is increasing. Vanadium, there is a slight decrease. It is maximum at chromium. Magnesium, it is decreasing. Ferric, cobalt, nickel. Then is copper and gold. Copper and zinc. Zinc is here. See, the melting point has decreased. So it increases, attains a maxima and then decreases. Because this melting point and the melting point is directly related to the covalence or the number of unpaired electrons in the d orbitals. In this case, say manganese and technetium have anomalous nature in melting points. Say manganese, it is drooping down. See, the manganese, the melting point is less, but it should be more, or it should be at least equivalent to chromium, because manganese, the configuration is 3d5 only. But if I talk of chromium, the configuration is 3d5-4s1, whereas manganese, it is 3d5-4s2. The electrons in the s orbitals are paired. So it should decrease, but it's showing more decrease in the melting point. So this is the variation of melting points in the transition elements in the series, and as in the say along the period, and as well as down the group, that is in the series. So this is 3D series, 4D series and 5D series. So this is all about this session, students. In the next session, we'll be discussing about the metallic character, about the ionization enthalpy, and also the oxidation state of these elements. I hope you have understood the concept I have discussed. It is, you must have done these concepts. This topic is actually very easy, students. You have to just remember one thing, that the properties of transition elements is due to the unpaired electrons present in the d orbital. So I'll be repeating that thing only while explaining each and every property. And questions come from this topic. That is why it is important also. So after listening this session, just go through the text so that you're through with the concept. Thank you students for listening patiently, and do have a nice time ahead.